Hello everyone, welcome to the video tutorial of the code. In this video, we will go over the tutorial notebook. To access the tutorial notebook from our official website, you can click on the resource on the top and then click the code to visit our GitHub repo. To open the tutorial notebook via Colab, click on the Open in Colab badge here. Colab provides free GPUs. To use it, click the Edit and click the notebook setting and then select GPU here. To start, we click on the two buttons here to install and load dependencies. The warp drive is the multi-agent reinforcement learning package for GPU users. If you are CPU users, please install the RLlib package. The code carbon is a package to track the carbon footprint. Please feel free to comment out any of them if not applicable. Here we take the GPU version as an example. To train a version without our negotiation baseline, please set negotiation on as 0. The warp drive will run multiple environments at the same time in parallel and give an ensemble result based on them. The trainer returns a logging of the evolution of all the desired variables from the last episode. The train batch size, number episodes, learning rate are for the training of the RL agents. It is worth noticing that we use PPO as the base RL training algorithm. The desired output is a list including all the interested variables to be output. If you want to run the simple negotiation version, please set negotiation on as 1. Now we introduce saving training results, plotting training procedures, as well as evaluations. Please uncomment these codes if you want to save the training results to draw graph later. Once the trainer finishes training, it will output a zip file including all the necessary scripts and all the training logs. If one wants to plot how the reward of each episode throughout the whole training process evolve, please run this block. As we mentioned, the trainer returns the time series of the desired variables. To plot dynamics of other variables in the last episode, please run this block. As illustrated, participants can either plot the time series for one variable or for multiple variables in a row. To quickly evaluate the results, please run this block. This will give you some basic information including reward, temperature rise, carbon mass accumulation, and some other economics metrics of your model. Now let's introduce a bit on the code structure. rise.py, riseq.py, risestep.cu, risehelpers.py. They are responsible for GPU version of the code. If you are using CPU version to train the model, the related scripts are rise.py and risehelpers.py. Now let's introduce them one by one. The rise.py includes the way that agents interact with the environment. This should be the main script to be modified. The risehelpers.py includes all the social economics and climate dynamics, which one probably should keep it unchanged. riseq.py connects the logic between Python script and CUDA code. risestep.cu is the CUDA version of both rise.py and risehelpers.py. If you are using warp drive, you should first modify rise.py and then find the corresponding function in the risestep.cu and modify it too. The CUDA code mostly follows the grammar of C++. If you want to add extra observations, you should add them in the generate observation function and the reset function. If you want to add extra actions, you should include them in the self.actionNVAC in the initial function. To implement the logic of negotiation protocols, for example, in the bilateral negotiation baseline, we have two steps. a proposal step for each agent to propose certain actions to other agents, and then an evaluation step for each agent to evaluate other agents' proposal. These functions describe how the negotiation actions affect observation space and the action masking. We will get back to explain action masking later. Both steps are done sequentially in the step function in write.py. Once the stage of negotiation protocol are concluded, the climate and economic simulation step function implements the social economics and the climate dynamics associated with the updated observation space and masked actions. We expect competitors to propose different mechanisms to encourage global cooperation among climate and economic objectives. Participants should therefore modify this code to match the logic of their proposed negotiation protocol, and even proposing new functions to replace proposal step function and evaluation step function. For example, competitors could propose a mechanism to form dynamic climate clubs based on a certain mitigate rate. Club members enjoy low tariffs when trading with other club members, while non-club members who do not contribute to mitigation enough suffer heavy tariff when trading with club members. Now, let's take a look at masking. Action masking determines the feasible subspace of the action space according to the negotiation protocol. Action maskings are set before agents choose their actions. So agents explicitly choose from the feasible action subspace. To implement this logic, action maskings are formed in the evaluation step after the proposal step but before climate and economic simulation step. In this way, the regions are prohibited from taking actions outside of the feasible action subspace. For example, during the bilateral negotiation process, if regions agree to implement a certain level of mitigation rates, they are required to do so. So, how to implement and modify the logic of action masking? The logic behind action masking is implemented in the generate action mask function. Mask dictionary gives the mapping from each region to its corresponding action mask. In the current implementation, mask is a binary vector where 0 indicates an action that is not allowed and 1 indicates an action that is allowed. For example, in the bilateral negotiation protocol, the action mask is based on minimum mitigation rate for each region. Please see the code below. Thank you for watching this video. If you have any questions, please don't hesitate to contact us.